This is lecture 22. So we were doing the partial derivatives. So we'll do few more questions on partial derivative and few rules for the partial derivative. So we have few notation, like if your function, let's say you have a function which is of x and y both, and we want to differentiate two times partially with respect to x. So we call it as curly square f upon curly x square, or d squared f upon dx. Sometimes we can also see it, and we may use the notation like fxx. Similarly, you can differentiate two times partially with respect to y, and we have another notation that we can differentiate f with respect to x and with respect to y as well. So generally what we say, we first differentiate with respect to y and then we differentiate with respect to x. So that's how it works. So similarly, if you have curly square f upon curly y curly x, that means curly of curly y of curly f upon curly x, right? So we can do a few more questions on this, and examples are there in exercise 12.3. So let's start from an example, and then we'll see those things. So example is, we need to differentiate with respect to x and with respect to y, and we have function which contains x as well as y in this form, right? So let's say if you differentiate with respect to x, so of course your y will be constant, so that becomes cos y plus y times ex, because the differentiation of ex is ex. Similarly, if you want to find out curly f upon curly y, right? So that becomes what? X minus sine y. Why? Because your x is constant, plus differentiation of y is 1 ex. So we are left with minus x sine y plus ex. Now, suppose we want to find out curly square f upon curly x curly y, right? So that is what? So you take the y first and then differentiate with respect to x. That means curly upon curly x of curly f upon curly y. So what is your curly f upon curly y? It's already there. We have already calculated this expression, right? So curly of curly x of minus x sine y plus ex. So you need to differentiate it again partially with respect to x. So that means your differentiation of this thing, as your y is constant, so will becomes minus sine y, because differentiation of x is 1, and plus ex will remain same, so it becomes ex. So that is the value of curly square f upon curly x curly y, right? Are you getting this?
सर
Is it fine?
सर
Yes.
इसमें जो
Yes.
करली स्क्वायर एफ अपॉन करली एक्स करली वाई सर उसका को हम पहले लिख रहे फिर तो वो भी मैटर करेगा.
वो मैं बताता हूँ कहाँ क्या मैटर करेगा, ठीक है?
ओके
मैं
सर.
बता देता हूँ. Okay, so let's see. So next one is, so now let's say we want to find out curly y curly x. So curly upon curly y, curly f upon curly x, curly upon curly y. What is curly f upon curly x? This is there, right? We have already calculated this. So this becomes cos y plus y times the ex. Now we differentiate with respect to y, so that becomes what? Minus sine y plus ex. Now, can you think of this thing? You have this one as curly square f upon curly y curly x, and here again, if you see this, so these two expressions are same, right? Can you see that these two expressions are coming out to be same? Somebody was asking that, does that matter that these two things will be same?
Yeah, no, sir, it will not matter the order.
It will matter, but in certain situation it will not matter. But we'll be dealing most of the times the cases when it will not matter. Okay. So what is that thing that I'll state only, will not do the proof of that part. Okay.
Okay, sir.
So when these two things will matter, when these two things will be equal, that is something we call it as Euler's theorem. Okay, so Euler's theorem on mixed derivatives, right? So I'll state only that part so that you'll keep in mind that when these two things are coming out to be same. And as I'm telling you, in most of the time in our course, we'll restrict ourselves to only the cases where curly square f upon curly y curly x is equal to curly square f upon curly x curly y, right? So what is that condition where these two things will come out to be equal? So that is if f of xy, right, and its partial derivatives. So which partial derivatives? Keep in mind its partial derivatives, that is with respect to x, with respect to y, with respect to xy, and with respect to yx. That these two things, okay? So are defined on an open region containing the point AB and are continuous and are all continuous at AB, then what? Then fxy is equal to fxy at AB is equal to fyx at AB, right? So what are those conditions which I want to state? What does that Euler theorem say? It says that when these derivatives should exist, first of all, these four derivatives should exist on an open region containing the point AB. This is one thing, that they should exist, right? They should be defined. So let me mark two special points. These four derivatives are defined. That is the one condition. On open region containing the point AB. Okay. Secondly, what? They all are continuous at point AB. So if they are continuous at point AB, then we say that these mixed derivatives are equal. Okay. But as I'm telling you, we will not be facing those conditions where these two things are not equal. So most of the time they are equal, right? Are you getting this? Is it fine?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Now let me start with a few questions from exercise 12.3. Let's say question number 1, that is fxy. We are asked to determine the partial derivative with respect to x and with respect to y. So let's say curly f upon curly x, this becomes what? 4x. And if we want to find out curly f upon curly y, of course that is constant, right? And 3y minus 3y will be minus 3. Of course, in both the cases, minus 4 is constant, so it will be eliminated, right? Is it fine?
Yes, sir.
Yes, sir.
Can we do this? Okay. So next one is, let's say question number 3, and that's what? F of xy is equal to x square minus 1 into y plus 2. So if we want to find out the partial derivative of f with respect to x, then we know that this entire portion will be treated as constant. Is it okay?
Yes. Yes, sir.
So that means what? So we can simply write it as 2x
2x
times
into
the
y plus
y
2.
plus. That's it. Okay. We don't need to take the product of that and then we'll be determining these derivatives. So this can be done directly. So similarly, if you want to find out the derivative with respect to y, then this whole factor will be treated as constant, right? So we can write it as x square minus 1 into 1. That's it. Okay. Are you with
Yes,
me on
sir.
this?
Yes, sir.
Yes, sir.
So let's say question number 15. So we have f of xy is equal to log of x plus y. So now, if you want to find out curly f upon curly x, so this becomes 1 upon x plus y into what? 1. And similarly, the partial derivative of f with respect to y will also be same, right? Are you with me on this?
Yes, sir.
Yes, sir.
Okay. So next, let's say question number 27. Okay. So we have three variable in this. So we have f of x, y, z. That is sine inverse x, y, z. So now,
So can
if
you
we
please
have
switch
three
to the previous
variables,
page?
yes, please. So if we have three variables, okay, even then it doesn't matter. So we want to differentiate with respect to x, we'll keep the rest of two as constants. So we'll keep y and z constant if we differentiate with respect to x partially. So in this thing, we'll take curly f upon curly x as what? So what is the differentiation of sine inverse?
1 upon
1 upon
minus,
under root 1 minus x square.
right?
yes,
Into
sir.
Yes,
partial
sir.
derivative of x, y, z, right? So that becomes what? Yz upon 1 minus x square, y square, and z square. True?
Yes, sir.
Yes, sir.
Okay. So similarly, we can also say that curly f upon curly y would be nothing but xz upon 1 minus x square, y square, and z square root, and curly f upon curly z will be nothing but xy upon 1 minus x square, y square, z square whole root. Okay.
Yes, sir.
Can we do this?
Yes, sir.
Okay.
Yes, sir.
Okay. So similarly, so you may get a new variable over there, but the idea will be the same. Let's say question number 37. That is what? If we have f t alpha is equal to cos of 2 pi t minus alpha. Okay, so this is a function which is in the terms of t and alpha, and let's say we want to determine curly f upon curly t. So our idea will be same. So that is minus sine 2 pi t minus alpha into differentiation of this quantity, right? So this is what? So since your alpha is constant, you will differentiate only with respect to t. So we are left with
2
2
pi.
pi only, right? And let's say if we want to differentiate with respect to alpha, even then the differentiation of alpha will be taken only, and your t will be treated as constant. So 2 pi t will be 0, and alpha's derivative will be minus 1. Okay, so we'll write it as curly f upon curly alpha as, so this is your cos, so that would be minus sine 2 pi t minus alpha into curly upon curly f alpha of 2 pi t minus alpha. So that would be what? Sine 2 pi t minus alpha. Okay, right?
Yes, sir.
Yes,
Yes,
sir.
sir. Yes, sir.
Okay. Okay. So now let's say, so this was 37. So let's say question number 43. So we have gxy as x square y plus cos y plus y sin x. We are asked that we need to find out the all second order partial derivative. All second order partial derivative means what? That means curly square g upon curly x square, curly square g upon curly y square, curly square g upon curly x curly y, and curly square g upon curly y curly x. Right? So these are the all second order partial derivatives which we'll be determining. Okay. So let's start with curly g upon curly x. So y is constant, so 2xy. Since your cos y is again constant, so 0. So that is your y cos x. Your y is in the product of the function of x, so it will be retained. So now you can find curly square g upon curly x square as well. So we are left with 2y only, and here minus y sin x. Is it okay?
Yes, sir.
Keeping y as constant and keeping y as fixed, and then keep on differentiating with respect to x, right? So similarly, we'll do another way, that means curly g upon curly y. So if you see this expression, now you need to differentiate with respect to y. So that means x square, so y's differentiation is 1, cos y minus sin y. So here your y is only 1, so differentiation of y is 1, so we are left with sin x. Right? So now you differentiate with respect to y again, so you know that these two terms will get eliminated. And differentiation of sin y would be cos y, right? So that means if you take curly square g upon curly y square, okay, so that becomes what? That becomes
Minus cos y.
minus
Cos y.
cos y. Okay, so similarly we can find out curly square g upon curly x curly y, which would be curly upon curly x upon curly g of curly y. And similarly we can find curly y curly x, which as I've told you, in most of the cases they'll be like same. Fair enough? So can you do this?
Yes, sir.
Yes, sir.
So what does it says? Chain rule, let's say for two variables, and then we'll extend it. And what is that? If w is a function of xy, that means only two variable, is differentiable. Let's say it's a nice function to us and it is differentiable, creates no problem. Let me put it more clear. Okay, so let's say w is equal to f of xy is differentiable, and x and y are differentiable functions of t, right? Then if we want to differentiate with respect to t, if we want to differentiate w with respect to t, so what we will do, dw by dt, that can be written as curly f upon curly x into dx by dt plus curly f upon curly y into dy by dt, right? So as I'm telling you, we will not go into the proof of that, So I'll do, I'll construct a picture, a tree diagram from which you can always infer that how the rule will get implied, right? How the rule will get implemented. So let me put it in that way, that your W is a function of XY. Okay. Then you have two variables, X and Y. So make two branches, X and Y. So we call it as intermediate variable. Okay. And then we put it here. Let's say here is you have X and here you have Y. Then your X and Y are further, they are further the functions of X. Okay, so let me put it in this way. So this is your T. So this is your dependent variable. Okay, always keep in mind this is your dependent variable, which is W. And these X and Y. Okay, they are your intermediate variable. Okay, so these are intermediate variable. So let me make it in this way, and this is your dependent variable. And finally, this T, you're differentiating with respect to T, that's why. So this is your independent variable. So this T is your independent variable. Okay. So let me make it more clear. This is your independent variable. Okay. So now mark the things that when you come from W to X, in this way, you'll write it as curly W upon curly X. Similarly, W to Y, curly W upon curly Y. X to T, dx upon dt. Y to T, dy by dt. W by dt will be what? So you take the multiplication of these two things. That means along the same branch, right? So this becomes what? Curly W upon curly X into dx by dt. And once one branch is completed, you have reached the T, take the second branch. So that means curly W upon curly Y and dy by dt. So take the product of these two, curly W by curly Y into dy by dt. So are you with me on this?
Yes, sir.
Are you getting this? Right? So let's say now try to make, if I have a function W which has three variables, X, Y, Z, and all are functions of T, right? And X, Y, Z are functions of T. Then how you construct the tree diagram? Can you tell me? Just tell me how many branches I'll make.
Three
Sir, three.
branches.
Right. So first of all, mark your dependent variable. What is your dependent variable?
W.
Yes. And similarly, yes, the W is your dependent variable. And how many intermediate variable you have?
Three.
Three, right? So let's say we make three branches over there, right? This way. Make me more clear. Okay. So these three branches will be for, their points are X, Y, and Z. And they are what? Tell me they are what?
Intermediate variable.
Intermediate variables.
Intermediate variables. And this is what your dependent variable. Okay, and if you have finally you have independent variable. Okay, so you are here your independent variable t, right? So this is your independent variable. So let us mark. So again with the same color I'm using so that it is easy to understand. Okay, so this is your independent variable and these three are your intermediate variable, right? So now try to mark the branches with the partial derivatives. So this is for curly w upon curly x, this is for curly w upon curly y, and this is curly w upon curly z. Now you want to go to x to t, so that means dx by dt, y to t, dy by dt, and dz by dt. Now you want to find out the dw by dt. So how you go? So take the first root, that is curly w upon curly x into dx by dt, plus first root is completed, take the second root, curly w upon curly y into dy by dt, plus finally curly w upon curly z into dz by dt. So are you with me on this?
Yes, sir. Yes, sir.
Right?
Yes, sir.
Yes, sir.
Okay. So suppose if I want to make it as a partial derivative, right? Let's say I want to make it as curly f curly w upon curly r. We'll be talking about that. That when you talk about the partial derivatives. Okay. So this, let's do one example on this. So after that we'll be dealing with the chain rule on the partial derivatives. Okay. So this is the example basically. So this is an example on page number 946. Right. So what does it say? It says that your W you have xy plus z. So x is equal to cos t and y is equal to sin t and z is equal to t. So can you think that which kind of chart is is more appropriate for this type of problem? Chart 1 or chart 2?
2.
Chart 2.
Yeah. So we have three functions, right? X, Y, Z, which are the functions of t, and we have one more dependent variable w, which is depending upon x, y, and z, and we are asked that we want to find out dw by dt. So how it goes? So we'll read this chart and we will determine the things. So that means we want to find out dw by dt. So that would be curly w upon curly x into dx by dt plus curly w upon curly y into dy by dt plus curly w upon curly z into dz by dt. Right? Is that okay? Are you with me on this?
Yes, sir.
Yes, sir.
So let's calculate these chunks which are present in the equation. So we'll be calculating these chunks and finally we'll be able to find out the dw by dt. So what is your curly w upon curly x? So just differentiate this thing partially with respect to x. What do you get?
Y plus
Y
Yes.
Y.
And what is your dx by dt?
minus sin t.
minus sin t.
Minus sin t. Right. And what is your curly w by curly y?
X
X only.
X.
And dy by dt?
cos t.
Cos t.
cos t.
Plus curly w by curly z?
1.
1. Right. So dz by dt, that is also
1.
1.
1.
So now you see that we want to find out dw by dt. So it should be in the form of t only, right? It should not get mixed with x, y, and z. So what we do, we'll rewrite the whole expression in terms of t. So what is the value of y? If you want to find out the value of y in terms of t, that is sin t.
Sin
Give it
t.
to us. So sin t into minus sin t, right?
Cos 2t.
So now what is x? Cos t into cos t plus 1. Now this is, so we are expecting that if it is in the form, if we are determining the dw by dt, So our answer should be in terms of t or at the most constant, right? So that becomes what? 1 plus cos square t minus sine square t. So in a more compact way, we can also write it as cos 2t.
Cos 2t.
Is it okay? Is it fine? So are you with me on this?
Yes, sir.
sir.
So
Excuse me, sir.
let me put the last result in for this lecture and then we'll be finishing the lecture. Yes, somebody wants to ask something?
Yes, sir.
Yes, please.
सर अगर हम एक्स वाई जेड की वैल्यूज उसमें पुट कर दें डब्ल्यू में और डायरेक्ट डी डब्ल्यू बाई डी टी कैलकुलेट कर लें
तो भी हो जाएगा, लेकिन सपोज अगर हमें ये पूछा गया है कि डू इट बाय चेन रूल, देन यू कांट डू इट.
ओके सर.
So should we move?
Yes, sir.
Okay. So let's see. Now keep your focus on this chart. Okay, so I'm changing a bit thing over here. That's what. I'm slightly changing, the question. That is what. So suppose you have a function w, which is of x, y, z. But now your x is some function of two variable r and s, and your y is also some function of two variable r and s, and again your z is also a function of two variable, that is again r and s. So earlier it used to be a function of t only, right? Now this is the function of r and s. Is it okay? Are you with me on this? Are you
Yes,
with me
sir.
on this?
Yes,
Now,
Yes, sir.
now keep in mind, so I'll make a small chart over here. Now think on this. So this is your W, here X, Y, Z. Okay, and let me make it over here. Okay, so we have three branches to the three intermediate variable, right?
Yes, sir.
But here, after getting these intermediate variable X, Y, and Z, now they are not dependent upon only R or only S, right? But let's say if we want to differentiate partially, so we'll make it as okay. So now let's say I want to make it a final variable to be R, right? Are you with me on this?
Yes, sir. Yes, sir.
Okay, so and I make another picture over here, and here let's say I want to have a final variable in S. So this is the partial derivative version of Euler's theorem. This is again a chain rule, but we'll be calculating the partial differentiation. So here we'll go from W to X, curly W upon curly X. So can I write it as dx by dt? Sorry, dx by dr. Can I write it in this way?
Yes, sir. Yes, sir.
Yes, sir.
No, actually. Why? Because your x is in the
आर एन एस का
two
फंक्शन है,
variable. Yes,
पार्शियल
yes.
करेंगे.
So, yes, so we'll write it as curly x upon curly r. Is it okay?
Yes, sir.
Right?
Yes, sir.
यस
So there
सर.
is no one dependent variable, na? That's why. So that is curly w upon curly y, and here earlier we used to write it dy by dt over here. Now we'll keep it as curly y upon curly r, and similarly curly w upon curly z and curly z upon curly r, right? Are you with me on this?
Yes, sir.
यस सर.
Yes.
And similarly, this similar kind of expressions are there, only your r will get replaced by s. Okay, so that is curly w upon curly x upon curly s, curly w upon curly y upon curly s, curly w upon curly z upon curly s. Is it okay? So how we read the picture? So rather than saying here dw by dt, we will not say dw by dt. So we'll say it as what? curly W upon curly R. Okay, so we'll write it as curly W upon curly X upon curly R, curly W upon curly Y into curly Y upon curly R, curly W upon curly Z upon curly R. Is it okay? Right? So you see the changes over here. Here you are now determining the partial derivatives, and here instead of dx by dt we are using the dx curly x by curly r. Why? Because your x, y, z are not a function of one independent variable. Now they are functions of two independent variables. Okay. So are you with me on this?
Yes, sir.
Yes, sir.
Okay. So similarly, do you want to find out curly w upon a curly x? You just replace your r by s. Is it fine?
Yes, sir.
Is it fine? So that's it for today.